A sub n not be equal to 0. So a sub n cannot be 0, so it can't be 0. Okay, it can't be 0. And the reason it can't be 0 is because you're going to divide. So what you do is you take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and you set that equal to L, right? You set that equal to L, okay? Set that equal to L. And there's 3 cases for the ratio test. So you take this limit, you have to have the absolute value. You pretty much use this in all of the homework. You use this on the test. Hey, Gibson, you're back. All right. Your mouse is in the other room. So, okay, it's in the thing over there. Yeah. And there's 3 cases, right? There's 3 cases. So the first case says if L is less than 1. So if L is less than 1, then we say the series converges absolutely. So we have what's called absolute convergence. So absolute convergence. So absolute convergence, right? Absolute convergence. If L is bigger than 1, then we have divergence. So divergence. By the way, by absolute convergence, what we mean is that if you take the absolute value, it also converges, right? So when you take the absolute value of the terms, you also get convergence. Whenever you have absolute convergence, you have regular convergence as well, so it's stronger. We don't have to be super concerned with it, but I'm sure you remember absolute and conditional convergence from other classes. And then the last case, I'll squeeze it in up here, is when L is equal to 1. So when L is equal to 1, anyone remember what happens in that case when L is equal to 1? Not undefined, close, no info. So no information, so no info. It'll never be equal to 1. If it's equal to 1, you did it wrong, right? Especially in this class, like something's wrong. Start over if it's equal to 1. It's moving again, yay. All right, so we're not going to do an example of this yet. We're going to wait to do a homework problem, okay? Because we're going to use it in the homework. So we'll come back to it. The other test, I guess this would be 8, is the root test. So the root test. And this only comes up briefly. Hey, Spencer! Root test. Root test. What's going on? You made it. You're back. Oh, no, it's okay. Oh, yeah. Mm-hmm. Right, because UCF doesn't have class. Yeah, no, we always have class. 5 days a week. So you let take the limit as n goes to infinity. And then this time you take the nth root of the absolute value of a sub n. So like this. And you set this equal to L. Right, you set that equal to L. And the conditions are very similar in this case, right? So I think it's actually the same. So if L is less than 1, we get absolute convergence. So absolute convergence. Okay, absolute convergence. If L is bigger than 1, we get divergence. So L bigger than 1, we get divergence. And if L is equal to 1, we get no information. So if L is equal to 1, I'll squeeze it in down here. L equals 1, we get no info. So these are the 2 tests that we'll mainly be using for all of the homework, right? These are the 2 main tests that we will be using for most of the homework. Let's go ahead and talk briefly now about power series, so you see what those are and you understand what a power series is. So power series, we're going to come back to this. This thing's always in the way. Like, here we go, game over. So power series. This is actually 9.8 in Calc 2, so it's probably been a while since you've seen this. Pretty much every single homework problem is a power series problem, right? Every single one. So this is a power series. We have an infinite sum. Okay, we're starting at 0. We usually start at 0.
Is this 9 or is this a different topic altogether?
This is the same. No, this is just a different topic. So we're done with the series test. Good question. We're not going to do the integral test, and we're going to be using these in the homework problems. So power series. So a sub n, x minus c to the n. Okay, this is a power series, and basically what this means is you plug in 0, so you get a sub 0, and then you get x minus c to the 0, so you get 1, so you just get a sub 0. And the symbol means you add, so plus. Then you plug in 1, so you get a sub 1. I'll just finish writing it, x minus c to the 1. I won't write it, plus a sub 2, x minus c squared, plus dot, dot, dot. Okay. We're going to be using these to solve differential equations maybe later today, definitely next week for sure we'll be doing DEs. Once we're done with this section, it's all DEs, right? And those problems are just insane. So this is called a power series. So power series. Anyone know what C is called? It's been a long time. I usually don't ask because I don't think. The center, good. Yeah, who said that? Good, Josh. Yeah, power series. It's the centered at C. Very good. Centered at x equals C. Centered at x equals C. So that's a power series centered at C. Something really interesting happens here that I want to show you. It's really cool. Watch this. Check this out. This is just an aside, nothing to do with the class, but it's really cool. So notice if you plug in C, you would get C minus C equals 0, right? This is really cool. So say you plug in 0 and say you plug in C. So if you plug in 0, you get A sub 0. If you plug in C, which you could do, right, you would get C minus C. So I'll write it. You would get C minus C, and then we said n was 0. So if n is 0 and x is C, right, if n is, hey, Ian, you look different. Why do you look different? Oh, no, it doesn't matter, sorry. That's just, it's good. Smarter. So if n is 0 and x is C, you get A sub 0. And check this out. You get 0 to the 0, right? 0 to the 0. Well, what is that? Well, 0 to the 0 is undefined, some people might say, right? But what we do is we make it equal to 1.
Why?
Because otherwise everything falls apart. so 0 to the 0 is equal to 1. I Googled this one day because I was curious, and some guy wrote like a 10-paragraph essay explaining why he thinks 0 to the 0 should be equal to 1. And so I always think, well, if it's not equal to 1, then all of this will fall apart, right? So just random. So whenever anyone asks you why 0 to the 0 is equal to 1, you could say that one reason is because power series will fall apart. Yes?
Well, anything to the 0 by definition
should be 1.
You also have other different.
Yeah, because 0 to the power of anything is 0.
Yeah, and if you put...
That's the whole paradox of it.
And what's infinity to the 0 with?
Yeah, exactly, right? So, and if you put this in the calculator, game over, it says error. Your calculator can't do it. So the calculator was wrong, and we're right, I hope. Okay, so that's the power series centered at C. So now I was going to go over the Power Series Theorem and explain it in detail. It's really cool, or do you want to just jump into the homework?
Really cool, I want to do it.
You really want to do it? You really? Oh, you really care? All right, let's do it. Let's do it. I was thinking about, if we don't do it, we can do an extra homework problem. Okay, all right, this is a big deal in mathematics. Let's do it. This is huge. This is huge. I almost didn't do it in my other class, and I did do it. It's so good. This is so useful. This is the Power Series Convergence Theorem. This is like a big deal. After this, we'll just do homework. Convergence Theorem. Power Series Convergence Theorem. And then after this, we'll start actually doing some problems, some examples. If you take complex variables at another school, it's a 4,000 level course, or complex analysis, you study all of this. You have a test on all of this stuff. And there's also this theorem. So we're going to do it both ways. So I erased the power series. It's here. So when I say for the power series, I'm talking about this one. So for the power series, starting to cool off in here now. For the power series, exactly one of the following is true. So exactly one of the following is true. So it's an interesting statement. Exactly one of the following is true. I just realized I haven't looked at my notes today. I probably should glance at them or something, right? It's like forget something important. So exactly one of the following is true. Yeah, I have notes. Yeah, it's good. So the first condition is that the power series converges only at x equals c. Say, what do you mean converges? Well, yeah, so if you plug in c, you get c minus c, right? We talked about that. And then this is you just get a0, and all of these are 0. So all of these go away, so you just get a number, so the series converges. So the first condition says that it only converges at c. So it converges only at x equals c, and nowhere else. Again, it should be noted that every power series in the history of the world will converge at C. Why? Because if you plug in C, this goes away, all of these go away, and you just get a sub 0, so the series is equal to a number, so it converges. So every single power series converges at its center, no matter what, right? You could just make one up, and it'll converge at that single number, okay? So this is saying it converges only there and nowhere else, okay? So that's the first That's the first condition. The second one is very deep, okay? The second one is extremely deep. Sorry that I erased it. I'm sorry. Sorry. All right, so 2. Do you already had it written down?
Yeah.
Oh, okay. Yeah, so 2. Should we use the fancy math notation? Yeah, we should. Yeah, okay. There exists, that's that backwards E, right? It means there exists. Remember that? Did we ever do this?
We did.
We did do this? We did? Oh, R greater than 0. So R is just a positive number. This is kind of cool because by going over what we're going over, this will bring to light some of the stuff you saw in Calc 2 perhaps that you didn't understand. Such that the series, so we're talking about the power series, converges absolutely. So converges absolutely. So absolutely. Okay, absolutely, in a certain interval. So this is worth doing, so check this out. It converges for the following values of x. So absolute value x minus c less than r. So this might not make any sense. We're going to go through it, right, because it's worth it, right? It's worth understanding what this means. And diverges for absolute value x minus c greater than r. Let me pause here and then we'll go through this. Okay, so it converges for this condition, whatever this means, right? This is actually an open interval, right? I'm going to show you exactly why it's an open interval. If you ever take more calculus, in particular like advanced calculus, you'll have to know exactly what this means. This might remind you of the delta epsilon definition, right? X minus c less than delta, or x minus a less than delta. That's the same thing. It's saying that x is within some interval, x is close to some number. Same thing here, x is close to c. Same deal. Before we do that, I hate to derail, but I never gave you the picture. I never gave you the pictures for the first case, like what it looks like, right? And it's going to seem silly, but there's 2 pics. The first pic corresponds to when we have real numbers. So the real case, so if we're dealing with real numbers, which we are, right? This is a differential equations class. The picture looks like this. It converges only at a single number, so C. Okay, so that's what it looks like for us. That's what it would look like in a Calc 2 class. Let me show you the complex case, just so you see, so you learn some more stuff. Because if you're going into engineering or any higher math, right, this is super cool, right? This is super useful. So a complex number can be thought of as an ordered pair. So you can think of a complex number as an ordered pair, or you can think of it as a plus bi, which can be written as an ordered pair, so a comma b. So that's kind of sloppy, me putting the equals there. So I'm going to smudge it and just put like a little squiggle. Same thing, right? So it looks something like this. So it converges at a point in the plane. So all of this can be done with complex numbers, right? Everything could be complex. So in the real case, it's a number. In the complex case, it's a plus bi, like 2 plus 3i, but which can be thought of as an ordered pair. Let's look at the picture here. Before we do, though, let's completely break this down. So what does this mean? So check this out. So we have that, right? So this is saying that the way I do it, well, there's 2 ways to do it. One, you can memorize it. One, you can think about it. Let's think about it first. This is a number whose distance from 0 is less than r, right? The absolute value of x is the distance between x and 0. So this is a number whose distance from 0 is less than r. So this number is between r and negative r. So when you drop it, you put an r. Yeah, you put a plus or minus. Yep, you put 1 here. Then you put the minus here. You memorize this in college algebra if you ever take that class, right? So like if you have something like this, you do this. In college algebra, you teach them to memorize. Oh, just memorize it. Whatever's a less than.
What was the reasoning again?
Oh, it's deep. Yeah, it's better to understand it. Good. So the reason is this. Here, let's think about it like this. And then we'll come back to that. X is a number whose distance from 0 is less than 2, right? So it must be trapped between 2 and negative 2, right? Same thing here. This is a number, and its distance from 0 is less than r. So it's between negative r and r, right?
Oh, it has to be greater than negative r.
Yes, yes. See, I just do it. I just say, when I see this, I say between, because I know already. But yeah, bigger than negative r and less than r.
Okay, cool.
We can add c to all 3 sides. You'll see the picture. It'll make even more sense. And then you get c minus r less than x less than c plus r. And now we can draw the picture for this interval. Hey, Jarrell, all right, get a haircut. Looks good. Yeah. So it looks like this. So here's c. Here's c plus r. Here's c minus r. and so it converges here. This has a name in Calc 2. They call it the interval of convergence. Yes, Matthew?
So does that mean that since r is greater than 0, does that mean that it converges absolutely with
Here.
less than 0? Diverges for something just greater than 0, like some number?
No, it'll diverge out here, and it'll converge in here.
Okay.
So this condition corresponds to this. So this is the pick. This is the real case. This is the real
But r
case.
has to be a positive.
Yeah, always. Yeah, because R is a radius.
That's what that here is.
Yep. So R is the radius. They call R the radius of convergence, which I'll write again down later. You might be wondering, why is it called the radius? Where's the circle? It's right here. This is actually a circle in the complex plane. Check this out. So the complex case.
The whole thing would be a diameter.
Yes. Right. So this whole thing here would be the diameter. So in the complex case, we talked about it. A complex number can be thought of as an ordered pair, right? So here's C. And it turns out that this means this is a circle, right? This is the inside of a circle. So here's R, and then here's your circle. It's beautiful, right? So now you see why it's called the radius of convergence. It's an actual radius, right? In Calc 2, they call it that, but in Calc 2, you don't have complex numbers. So you just say, oh, it's a radius. Yeah, I believe it. Now you see why it's a radius. This is called an open disk because it's two-dimensional. If it was three-dimensional, it would be an open sphere. And if it was four-dimensional, then we just call it an open ball, right? We call them all balls. You can just call them balls if you want to, but it's an open disk.
And you were saying the backwards ER means that there exists a real number greater than 0?
Yeah, R is just, we use R for radius, but yeah, it is a real number, yeah. So basically,
There's just a radius that's greater than 0.
yes. Yeah, so far 2 cases. It converges only at a single number, or there exists some small positive number, maybe big, where it converges somewhere near that number. And the third case is the easiest case, is that it converges absolutely for all x. So it converges absolutely for every single value of x, right? It's a strange sound, isn't it? Converges absolutely for all x. So there's 2 pictures here. So the real case would be that it just converges everywhere, right? At every single number. And the complex case would be that it converges everywhere in the complex plane, so at every single number, right, everywhere. So those are the 3 cases, and this is called the convergence theorem or the Power Series theorem. Some people just call it the convergence theorem. It's that big of a deal in mathematics. It's in pretty much all the books on series, right? It's in your Calc 2 book. It's in every complex variables book. So it's the same. So it's actually the same. So if x is a complex number, it's exactly the same. So now you know some complex variable stuff. This is almost done. Then we'll do an example. There are some important names that I mentioned that I didn't write down. So R is called the radius of convergence. So R is the radius of convergence. So radius of convergence, right? And now you see why it's called the radius of convergence. It's an actual radius, right? It's an actual radius.
So the complex case actually exists. Wouldn't the radius be infinite?
In some cases, let's talk about that. Well, let's talk about that. Let's see. So I'll jump to that. Let's jump to it right away. So in 3, the radius is going to be what? It's just going to blow up. So it's going to be infinity, right? Right? Because here's C. See, if you look over here, here's R. So if R gets infinitely big, it ends up converging everywhere, right? In 1, let's look at what R would be in case 1. So case 1 is over here. So this is the first case. What do you think the radius should be here in this case intuitively? 0. Good, Ian. So R is 0. Good. So there is no radius, right? Because it's converging only at a single number. So here it's just positive, right? Here it's 0. And then here it blows up and it converges everywhere. I didn't put C in the picture. I could have put it there. There's C, just for reference. And last but not least, the set of all x, just so you have it in your notes, the set of all x for which the series converges, is called is called, it has a name, right? It has a name. It's called the interval of convergence, right? You might say, well, in this case, it's not an interval, right? Yeah, in this case, it's a disk, right, or a region. But we just use the word interval because we're typically dealing with real numbers. It's called the interval of convergence. So the interval of convergence, Beautiful stuff. So that took like, I don't know how long that took, maybe like 10 minutes. I think it's worth it because this way you have in your notes. Yeah.
Can I figure out what C is? Is that where you center?
Yeah, C is the center, yes.
And then the radius is anywhere like adjacent to that C?
So pro.
So that if you were to pick any point within that radius,
It converges there.
it converges
Yep.
inside that disk now.
Inside that disk, is that, yeah, we said, yeah, disk.
So then you can take C and move it anywhere you want, right?
Right, and you get different series though.
And you get a different series, but anywhere inside that disk where you move it, the power series that is created by that center and that radius converges.
Absolutely perfect. Yep. Beautiful. Sometimes it has to be a certain place, but for our purposes, things will converge usually. Well, you'll see. They'll give us the power series in the homework. They'll give us the center, and we just have to find the radius. That's what we're going to do next. So like so it will converge everywhere in this set here. So let's do a homework problem. Let me just sign into the homework. So let's do one. Let's make it count. Let's do like a good one. Let's do it. Let's do like a great one. That's worth doing. By the way, I'm pretty much done with your take-home test. I just haven't posted it yet. I just want to look at it one more time. So you'll have one like this on your take-home test, very similar. So number 4 from the homework.
Quickly, will our in-class test be smaller?
Yes. Yeah. Oh yeah. Yeah. It's really small. I already started working on it, but I almost printed it, but then I hesitated because it was really small. Like it's really, yeah. I don't know. Do you want it small or?
I prefer it smaller.
Really?
I don't know.
Yeah, I mean, I don't know. It'd be worth a lot of points still. I mean, I'm thinking like, do you guys want 2 DEs or 3 DEs in your test? I guess you don't know yet, right? So. Maybe, yeah, I know. The one I have now only has 2 DEs. I'm like, oh, they're going to finish in 30 minutes. But that's okay, right? Like, it's Christmas. So infinite sum. Plus, the take-home is hard. Like, the take-home is like, so k equals 1 to infinity.
What allows us to study for
6-1. Also, you can study for the final, you're right.
When's the final?
The last day of class.
Isn't it 6, like 2 days?
1 over k squared plus k. Wow, that's when it is. So far, I know, it feels like we're never going to get there, right? You can take it early if you want, although I don't know if I'd recommend it. 5x minus 1 to the k.
Wait, so the next test is the last test, right?
No, we have the next test and we have the final still.
Well, I mean, besides the final.
Yeah.
So the test in a week is
Yeah.
the next test in 2 weeks, so it's like other stuff.
Yeah. Yeah, I think so, yeah. Yeah. All right, so the question is to find the interval and radius of convergence. I don't know when I don't think your test is next week, is it? It's not.
No, the homework's due on the 20th.
No, I need to change that. I just clicked the button because it wasn't set up when I walked into class. I'm like, so I just, yeah, it's due like, yeah, it's 2nd of December? Yeah, that's when it's due, December 2nd.
Yep, December 2nd.
It's far.
Pulled it up, so.
Sorry. Yeah, you can take it early if you want, but okay. Find the interval and radius of convergence. So interval and radius, of convergence, right? Interval and radius of convergence. So the first thing you want to do in a problem like this is just use the ratio test, right? So I'll show every step. We'll go slow. So solution. SOL means solution. So limit, LIM. And then we have k instead of n. So I'm going to go ahead and use k. Okay, so k goes to infinity.
This is the actual number 4 problem in this one.
It's our first homework problem after like a day and 29 minutes. So sorry, but it's all right. So we have 1 over k squared. Fail. Absolute value. A sub k plus 1 over a sub k. So that's the ratio test, right?
Are you recording right now?
Yeah, it is recording.
That's pretty cool.
Yeah, it's kind of messed up though. Like it's supposed to. Yeah, it's not following me because the guy who let me borrow this, I'll just delete this so he doesn't read this. The guy who let me borrow it, he asked for it back like yesterday, so this is a new one. And, yeah.
Are you doing this week?
It's on there. The lecture you missed is on there. It's been posted. So last time is on there. It's on the channel. So this is equal to the limit as k goes to infinity. So this means you replace all of the k's with k plus 1s, right? So I'm going to leave the absolute value there. We do need to leave it, right, because we have an x, so we can't drop it, right? Because you don't know if x is positive or negative. So it'll be, so I'm just going to go ahead and plug in k plus 1s and write it like this. 1 over, actually, I'm going to put this up here. So like this, 5x minus 1 to the k plus 1 over, and then k plus 1 squared, k plus 1. So k plus 1 squared plus k plus 1, just like that. So the only thing I've written down on the board so far is a sub k plus 1, right? That's the only thing we've written down so far on the board, right? Now we're dividing by a sub k. So when we divide, what do we multiply by? What is that called when we flip it? The reciprocal. Yeah, so let's flip it. So it'll be times k squared plus k over, and then you have 5x minus 1 to the k on the bottom. So 5x minus 1 to the k. And then you still have the absolute value. So let me pause here because it's tough when you're first learning this, right? This is a tricky step. And again, you do this in Calc 2, and maybe it's been a while since you took Calc 2, right? Maybe it's been a while. Spencer, it's been like a couple of years, right? Like since 5 years now? Yeah.
It's been almost 5 years.
Yeah, he was in my Calc 2 class 5 years ago. Like, oh, it's a legend. It's good. It's so cool. All right. Yeah.
How did you know 2 was n? So with a ratio test.
Oh, just whatever is there. Whatever letter is there. Like if it's an I, you would use an I.
And then, so let's say I'm doing this problem in our homework. How would I understand to use the ratio test? What are key signs?
I would just say to find the interval and radius of convergence. You could always use the ratio test.
Oh, for both of those?
Yeah,
So
always.
when it asks for interval and radius,
Just ratio
test will give you both?
Yeah, you can use that. Just start off with that. There's one in the homework where that's geometric, but I mean, yeah, you could use this too. Okay, at this point we can do some math, right? So this and this, there's going to be some cancellation. So I'm going to do it up here so you see it. So I'm just going to go to the side and rewrite this. This is 5x minus 1 to the k plus 1 over 5x minus 1 to the k, right? 5x minus 1. Yeah. Yep, just a 5x minus 1 up top. It's exactly right. Because you can write it like this. Right, and then these cancel, so you just get 5x minus 1. Boom. So sometimes people don't know that. Like when you first take Calc 2, you're like, oh my God, how does that happen? Like this is like a confusing step. So in case you forgot, so we're left with limit. K goes to infinity. So here we have absolute value, parentheses 5x minus 1. And I'm going to go ahead and just rewrite these again. So we have k squared plus k, and then we have this piece down here. So we have k squared plus k over, and then we have the bottom piece, k plus 1 squared plus k plus 1, parentheses, absolute value. So we're there. So we are there. Can you see better there?
Well, I don't know yet. I'm confused on how you went from
Here to here?
Yes.
Okay, absolutely, let's do it. So basically you put a k plus 1 everywhere there's a k, right? So here we put a k plus 1, boom. Here we put a k plus 1, boom. Here we put a k plus 1, boom.
Okay, because that's just the numerator.
That's just the numerator. Then we're dividing by this. So what we did there is we just flipped it.
Okay.
Took a shortcut.
Now I see.
You see? No, it's worth it. Ask. No, it's your life. It's good. Yeah, it's good.
So then, I'm still struggling a little bit. You put
K plus 1 in.
Power Series, and you shove a k plus 1 in anywhere you
See
see,
a K. Anywhere you see a K.
and then you take the reciprocal,
Yeah, because you're doing, and then just put it there.
exact same thing.
Just
so
flip it.
Instead of a k plus 1, you shove in a k,
Always.
and then you multiply across them.
Yeah. Multiply across. Usually stuff cancels. Stuff with the x's will usually go away every single time. Yep, every time. And once you do one of these on your own, it's like you got this. Like you'll become like a master at it. Yep. So now at this point we're going to take the limit, right? So the 5x minus 1 is independent of the k, right? There's no k there. That's just going to hang out. And then so we're just basically looking at this piece here, right here. We're looking at this. So we're looking at the biggest degree terms. So in the numerator, it's k squared. In the denominator, if you multiply this out, you're going to get a k squared here, right? So it's kind of like you have k squared over k squared. So it's just going to be 1, right, when you take the limit. So you're just left with absolute value 5x minus 1. Because this is the limit, and all of this is going to approach 1, right? All of that's going to approach 1. Does that make sense? All of this is just going to go to 1, right? Because it's k squared, and then here you also have a k squared. It's like if you were to multiply it all out, you would get like, k squared plus k over k squared plus some stuff, right? So then it's just 1 over 1. It's the ratio of the coefficients, so you just get 1, right? So we're here. Pause here. This is like one of the hardest things in Calc 2 for people, so that's good.
How could I write that in a note? What you just did?
Basically, just do this, put the arrow here and put a 1. So like, because this goes to 1, right?
Yeah.
Do you see why?
Yeah.
Mm-hmm.
Because it may as well be k squared over k squared.
Boom. Just 1, like a pro. Like a pro. Wearing the same shirt. Oh, not quite. They're very similar. It's good. It's good. Extra credit. I'm kidding. All right, so we're here. So we wanted to converge with the ratio test. So when you want convergence with the ratio test, do you remember what it has to be less than? Do you remember less than for the ratio test?
R, right?
Yeah, well, R, but what 1. 1. Remember the test? It said you had L less than 1 converges, L bigger than 1. I used to never understand this when I was in calculus. I would just memorize it, be like, oh, I just do that because that's what we're supposed to do. This is your L, right? This whole thing is your L in the ratio test. And you want it to converge. You want convergence, so you set it less than 1, right? The ratio test says that if this limit is equal to L, and if it's less than 1, it converges, right? So we force it to be,
We're gonna know it's less than 1.
No, we want it to be less than 1.
So we're just saying it.
We're just saying that. That's right. Good. So we don't know. So you hear what Spencer asked? He said, how do we know it's less than 1? We don't know. Right? We want it to be less than 1. It's forced. That's the same question I had when I was in Calc 2. I'm like, well, how do we know it's less than 1? And I would just put it there every time, and it's whatever, and I got an A, and I was happy. But I never understood it, right? It's because we want it to be less than 1. Why? Because we want it to converge, right? We're looking for convergence. Remember, if this is equal to L, if it's less than 1, it converges. So we purposely put this
Why
here.
are we looking for convergence and not divergence?
Oh, because the question wants the interval of convergence. Good question. Oh, that'd be nice. No, I wouldn't do that to you. Find the interval of divergence. No. It's like game over. No, I would never. That's just mean. All right, so now we got to solve this for x. That's, yeah. Oh, that's so bad. So you have this, 5x minus 1. Oh, this part here is really tricky. This is greater than
Negative 1.
-1. Yeah, be really careful in this step, right? It's really easy to mess up there, right? Really easy to mess up. So whenever it's less than 1, you put a positive and you put a negative. You have to put both, right? You have to put both. If you mess this up, it's pretty bad, right? Because it's going to cause a chain reaction. So then you just add 1 to all 3 sides. So plus 1, plus 1, plus 1. So you get 0 less than 5x. Less than 2, less than 2, less than 2. Then we just divide by 5. So we end up with 0 less than x less than 2/5. So we're almost there, right? Not, well, kind of. We're like halfway there, right? We're like halfway there. So that's the interval of convergence, kind of. We just don't know what happens at the endpoints. I don't know if you remember, but when it was equal to 1, we had no information. Do you remember that? So let me just show you something here so you really understand, because no one ever talks about this. So when it's equal to 1, look what happens. If you set it equal to 1, we have no info. If we set it equal to 1, we have this. If we set it equal to 1, we have this, or we have, I'm going really fast, or we have this. So if we set it equal to 1, I usually don't do it all, but I'll just show you. So if we set it equal to 1, you can do some math, and you get the endpoints. These are called endpoints. So when it's equal to 1, you get the endpoints. So when it's equal to 1, you have no information via the ratio test. So we have to check the endpoints. So you always have to check the endpoints when you get here. Okay, so the ratio test tells us that it converges whenever x is between these numbers. But when it's equal to 1, we get the endpoints. And when it's equal to 1, we have no information. Therefore, we have to manually check. So that's why in calculus 2, they always say, oh, you're supposed to check the endpoints, because the ratio test doesn't tell you anything about the endpoints. That's why you're supposed to do it. Okay, so that's what we'll do. So whenever you get here, you just check the endpoints. All right, let's, yeah. Oh,
You check the endpoints by shoving them into your original 5x.
into this one, into this beast. Yeah, we're going to go back in here now. Fun times. Let's do it. So now we're going to go back to this one. So now we're going to check 0. So let's do it. This is why we had to go over all those series tests last time, right? Yeah, it's a lot of work. It's good, though. It's good. Build character. This is like, check 0, check 0. Yeah, this is good. I love it.
Could I write like x?
Yeah, maybe I should do that, too. Yeah, let's do it. Let's do it. Check x equals 0. Why not? Good, Patrick. Yep, worth it. Yep, good. Yeah, because that's what we're doing, right? We're plugging in 0 for the x. So we have infinite sum k equals 1 to infinity, 1 over k squared plus k. All right, and then we're going to plug in 0 for the x. So we have parentheses 0 minus 1 to the k. Oh, I see, said the blind man. It's a little bit harder than I thought it would be. I'm like, oh, wait a minute, huh? Yeah, I didn't expect that. I zoned out. I was thinking about something else, and I was thinking like, oh, it's going to be easy. No, I mean, it is easy, but like, yeah, I thought it was going to be like really easy. Yeah, there's some work. Yeah, it's an alternating series. Yeah, alternating series. Fun times. AST. All right, so now we can use the alternating series test. So whenever you're using the alternating series test, you start off by defining your a sub k or your a sub n, right? So here it's a sub k. So I'm going to use set. I'll use the word set, a sub k. So a sub k is always the non-alternating part, right? So it's just this part. Okay, 1 over k squared plus k. All right, that's the non-alternating part, right? Always. It's your non-alternating part. And then you just have to go through the motions, right? You just have to go through the conditions. This is our second, it's been a while maybe since we've done this. We did it last time, but we only did one example. So the first step is to take the limit and just see what you get. You should always get 0, and we do. That's the first condition in the alternating series test. That when you take the limit of the non-alternating part, you get 0. I don't know if you remember from last time, what happens if you don't get 0 here? It's kind of a hard question. What test do you go back and use? Do you remember? Oh, yeah, that's it. The nth term test, very good. Very good. Yeah, most people don't know that. Good. So if you don't get 0 here, you go back and start over and use the nth term test, and you'll get divergence. Every time, right? It will always work if that's the case. 2, this is the uncomfortable part. I always think about Patrick now because you mentioned this last time. A sub k is, what are you supposed to say? Do you remember the word? Non-increasing. Yeah, that weird word. Yeah. Because non-increasing is decreasing or staying the same. I used to have such a hard time with that when I first saw that word. I'm like, why can't they just say decreasing? So both of these conditions are satisfied, so we have convergence.
How do we say that they're non-increasing? How do we say that they're non-increasing?
Yeah, it keeps going down, and it does this. Just, Yeah, you could take the derivative and show it's negative, but
No, just logically. I mean, if it's going every time, as I'm getting closer to
And
infinity, it's getting infinitely smaller.
it is, and it's always positive, so it's just. Yep. So converges. So converges by the. What test what do we use? Nope.
No, AST.
Alternating series test. Yeah, good. AST, by the AST. So that means we're going to use a bracket at 0. So over here, when we write our answer down, I'll start writing it up here. We're going to use a bracket at 0, right? Because we include it. If we had divergence, we would use a parentheses at 0, right? We would use a parentheses at 0. So, any questions so far on this one? Any questions? I didn't think we're doing really good on time. Like my other class, like they had a whole 2 hours and 45 minutes, and like we must have gone faster last time or something. This is really good. It's good. We have like tons of time. It's awesome.
So when we check 0, we use the alternating test. So the negative one.
Yep. And I know it's obvious. Like after you get really good at it, you're like, oh yeah, it's convergent alternating series. But just go through the motions and say it. So you say it. Eventually it'll become obvious. I mean, many of you probably saw it and say, oh yeah, it's going to converge alternating series. Okay. Now we have to check 2/5. That's the other endpoint, right? So let's check it. So let's check, and I'll stick to what Patrick said. X equals 2/5. That's a little bit more descriptive than just saying 2/5. It reminds you where to put the 2/5. I like that. So you got to go back in here. A common error on exams and stuff is people forget to write the sum sign. I know it's kind of like tedious, but so k equals 1 to infinity. We have 1 over k squared plus k. Then we have 5 times x. X is 2/5. So we have 2/5. 2/5.
Which is 2.
Minus 1, which is just 2, right? Which is just 2. Yeah, it's just going to be 2 because the 5s cancel, right?
2 minus 1 is 1.
2 minus 1 is 1. And 1 to the k is just 1, right? So it's just going to be interesting. Oh, okay. Okay, not so bad. So we have 1 over k squared plus k. So because this is just 1 to the k, this piece here. So which is just 1. So it just goes away. So it just goes away. Goes away. Good stuff.
So does that go to 0? Right?
Yeah, it goes to 0. So, but that doesn't tell us anything, right? Remember, if it's not 0, it diverges. So we can use direct comparison for this, right? It's almost like a p-test, p-series, right? If it wasn't for that annoying k. So let's just use direct comparison. So we'll write it down. And when you're trying to show convergence, do you put a less than or do you put a greater than? Do you remember what to do there? What is it? You remember what to put? Do you remember, David? Less than. Yeah, it's a less than. I'll put a less than or equal to be safe. You could use limit comparison as well, but it's just easier to use direct in this case. And then you can drop the k. The reason you're dropping the k is because you want to compare it to 1 over k squared, right? Boom. Then you have to explain why the sum of these terms converges. So and, by the way, this inequality is true, right? This fraction is smaller than this one because
Dividing by more.
you're dividing by more over here. Good, very good. And then this sum, k equals 1 to infinity of 1 over k squared, is a p-series.
Yeah, it converges because it's greater than 1.
Let's just say it that way. Let's just say the way you said it, is a convergent p-series. Yeah. And let's just emphasize why. So is a convergent p-series because, new notation, I just made that up. No, I didn't, I stole it. Because. Have you ever seen that before? Oh, you have? Oh, okay, okay, so p equals, what's p in this case?
2.
2, and it's bigger than 1. So we have convergence, yep.
I'm a little bit behind. Is the test you use the limit comparison?
We're using direct comparison. Yeah, we're using direct comparison. It's okay, I'm gonna go over it again. So, we see this, we get here, right, and we say, okay, it's almost like a p-series, except it has the annoying k. So we write this down, and we create a less than or equal to, and we drop the k, right, because this is smaller than this, and then we just have to explain why this converges. So therefore, so thus, our guy here, k equals 1, this series, k equals 1 to infinity of 1 over k squared plus k. So this one converges by the, what test would you say in this case? Direct comparison test, by the DCT. By the DCT. By the DCT. I keep thinking that thing is going to fall. Hear it squeaking when it moves? Yeah. It's speeding up. Come on. Any question? Oh, does that mean we use a bracket or a parentheses at 2/5? What is it? Bracket. Yeah, what if it had diverged? What would we use? Parentheses. So this is the interval of convergence. This is it. This is the interval of convergence. Almost done, right? Almost done with this problem. Almost done. We're almost there. Wait till we do a DE. You're gonna be like, oh my God, like, yeah, like the DE, one DE will take us, in 6.2, one DE will take us 45 minutes. This is the reason you have a part take home. It's not because, oh, I want to give them a take home. No, I have no choice, right? Like, otherwise, like, you only have like easy, on your test, it's only the easy problems, right? It has to be the easy ones, because I mean, you only have an hour and 15 minutes.
So we got to find the radius.
We got to find the radius. So there's two ways to do it. There's the weak way and the cool way. Well, it's not the weak way, but the way I don't like to do it is you can add them up and divide by 2. I think that'll give you the radius every time. I like to draw a picture and like really overthink it. You know, like let's do that. Let's look at it visually. So here. So, oh, my way also requires more thinking.
Oh, good.
It's even harder than I thought. Okay. Wow. We have to find the center of this thing, right? So to find the center of this, it's beautiful. So watch this. I'm just going to focus on this. You can do this. You can pull out a 5 in a really uncomfortable way like this. Oh, I love this. Look how confusing that is, right? 5x. 5 times 1/5 is 1. This never comes up in Calc 2. I mean, at least not in my class. And then look, this is 5 to the k, x minus 1/5 to the k. So you see your center is 1/5.
Brilliant.
You could just set 5x minus 1 to 0.
I was waiting for it. Yep, you could do that. Absolutely. So Matthew's way. I can't spell your name. Matthew's way. So Matthew's way is you do this.
Oh, I think that's why I didn't count 2.
Yeah, most people do that, but it's fine. It's whatever. I like to do it like this, so that works. Uh-huh.
I saw that logically, but why can you do that?
Why can you do the what? Which part? The 0 part?
Set it equal to 0. I mean, you can see it, that it happens.
Yeah, I mean, just think about the basic case. If you have this, right, x equals c is the center. So when you plug in the center, it's always 0. So you just make it 0 and then just solve for your center. It should always work. It's the same thing, right?
Oh, so the center collapses.
So is that not the easiest way then?
Which way? Matthew's way? Yeah. It is, but I like to draw a picture. So let's go back to my way. So here's 1/5, and then so here's 1/5, and here's 2/5, and here's 0. So now we can see the radius. It's right here. Look. Ha! Right? Isn't that cool? So what's the distance between 1/5 and 2/5? What is that going to be? Just 1/5. That's the radius. That's it.
And so you could legitimately just draw a circle around the 1/5 as the center.
Yeah.
As your endpoints of your circle, and then anything inside that circle would converge?
If you were dealing with complex numbers, yeah. So if you're dealing with complex numbers, you'd have a circle here. Yeah. But we're dealing with only real numbers, right? Yeah, we're only dealing with real numbers. Yep.
You
So-
get complex off of it.
Yep.
Okay, that makes sense. Thank you.
Yep. Any questions on this one? So that is the problem. That's it. That's it. So let's do something else then. Let's do something else. Let's briefly talk about Maclaurin series briefly. So there are, yeah, me too. I love Maclaurin series. So don't worry, we're just going to touch on them. So there's 3 of them you should have memorized for your test. Just 3 of them. So
cool deriving the sign from the Maclaurin series.
oh, you derived it? Oh, those are good memories. That's good. Maclaurin series. So briefly talk about them, do a simple example, then we'll move on to something else. We're doing really good on time. We're going to be able to do an example of a shift today in class. So that's really good. Do a shifting problem. So there's 3 Maclaurin series you want to know for the test. So the first one is the Maclaurin series for e to the x. Yeah, this one's beautiful. X to the n over. Yeah, this is life. Yes, this is great. So you have to know it 2 ways. You have to know it that way, and you have to know it the other way too. You may say, what do you mean the other way? You have to plug in the numbers. So I'm not going to plug in the numbers, but you can if you want to. I just have it memorized. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. So we have, that's the Maclaurin series for e to the x. So you might be wondering, why do we need it? On your test, on your in-class test at least, every single question will say, write your answer in terms of familiar functions. So after you get to the end of the problem, you have to recognize the pattern and know it's like an e, a sine, or a cosine. Or maybe it'll just be x squared or something, right? So everything will be familiar. You'll get nice answers, right? You'll get nice answers. 2, the second one.
When you finish your differential equation, you're going to get 1 plus x plus
Yes.
plus, and you have to recognize that the Maclaurin series of a particular function.
On the take home, it's harder. Like it might be the Maclaurin series of e to the 3x times 4 or something like, oh, but on the in-class, it'll be easier.
How would you recognize it?
Just by noticing that, by memorizing that. And you'll know on the test, it'll say, write your answer in terms of familiar functions so you know to look for it. Okay. Yeah, it's really hard. There's some hard patterns. That's why I'm keeping it to only 3.
And this is what's going to be on your take home.
Also, yeah, both. Yep. Cosine. The Maclaurin series for cosine is really interesting, and there's an easy way to memorize it. Is cosine an even function or an odd function? Anyone know? Even. It's even. Yes, it has only even powers of x. So it looks like this. -1 to the n, x to the 2n. I almost messed up and put parentheses. And then here we have 2n factorial. So cosine is an even function, so it has only even powers of x, right? That's the best way to know it, I think. Plus, this way you know it's even, right? What does it mean to be even? Even means that when you plug in -x, you just get cosine of x. So even functions eat negative signs. Also, even means that it's symmetric across the y-axis. Just extra life knowledge. Why not? It's college, you're supposed to learn stuff. So here's why. If you flip it, you get the same thing. It's supposed to be symmetric. I messed up. It's a terrible picture. So it's a really weak picture. It's a terrible picture. It doesn't matter. Okay. Oh, what is the first even power of x. Not 2, but what's another? 0. So you just get 1. X to the 0 is 1. And then what is the next even number after 0? 2. So it alternates. So it's minus. This is how I memorize it. See, first it's x to the 0, and then it's 2. And the next one should be 4. But it alternates, so it should be plus. I'm not actually plugging in the numbers, right? No way. I mean, you could do that. You could plug in the numbers and work it out. But then that's more work, right? So it's x to the 0. So 0, 2, 4, one more. So just to make sure you got it, what would the next one be, minus or would it be plus? Minus. And what would the power be in the next one? 6. This is super useful. So by memorizing it this way, not only do you know the power series, but you know cosine is even. So like it opens up the door for more stuff, right? So kind of cool. So cool.
No, that one, actually, no, that one was, oh, okay, I see now, that one.
See it? Then we have the sine function. So sine x also starts at 0. All of you start at 0. All of you start at 0. So sine x also starts at 0 as well. And so this is negative 1 to the n. It has that.
So does that mean if cosine's an even function, sine would be your odd one?
Sine's the odd one, absolutely. So sine's the odd one, so we're going to...
They're inverses, right?
They're not inverses, but one's a translation of the other. Yeah, 2m plus 1. Yep, boom. 2m plus 1, and then we have 2m plus 1 factorial. So from math, whenever you have an even number, it can be written as 2 times n. Whenever you have an odd number, it can be written as 2m plus 1. So if you know that, then you know it's 2n. If you know odd numbers are 2m plus 1, then you know it's 2m plus 1. So you can know, if you know, it makes you learn a lot of stuff. What's the first odd number bigger than 0? What's the first odd number? 1. So it's just going to be x to the 1, right? And the next odd number would be 3, and it alternates, so it's minus, right? So minus x cubed over 3 factorial. Boom. It's really nice knowing it this way. And then the next one is plus, right? So plus x to the 5 over 5 factorial, and then minus dot, dot, dot. So those are the ones you have to know. That's it, right? There's more in the homework. You have to know more for the homework, but let's just do an example so you see how you would have to use it in the homework. So the homework will have questions like I don't know, something really easy like Maclaurin. Oh, I misspelled it. Maclaurin Series for, I don't know. Here, I'll just pick one from the homework. Let me see. Yeah, okay. Well, it's kind of an annoying one. That's good. It's good. It's good. It's good that it's annoying, I guess. So this one, it's got a fraction, so it's no fun. So something like this. So solution. So if you're doing something like this, the first thing you do is you write down the Maclaurin series for e to the x, right? So you write that one down first, okay? So you have e to the x equals infinite sum, n equals 0 to infinity, right? X to the n over n factorial. Okay, so you do that first. So we do that. And then all we have to do now, it's really easy, is you just replace x with negative x over 5. That's all you do, is you just do that. So like this. Just like make a substitution. I think this is really easy, like super easy. Like really, sometimes people get this wrong in the Calc 2 test. I'm like, how? Like, no, it's like one of the easiest questions. So all you do is replace it. There is some math here. It's going to get a little bit messy, but so instead of x, it'll be this. So it'll be this. This is where we have to do some work. Uh-oh. There we go. Boom. So this. So we should clean it up a little bit, right? Just a little bit. So to clean this up, what you can do, I'll go to the side and do it. If you have negative x over 5 to the n, to show all the work, you could write this as negative 1 times x over 5 to the n. So you just basically raise everything to the nth power. So you raise the negative 1 to the nth power, you raise the x to the nth power, and you raise the 5 to the nth power. So I just do that in my head. I raise them all to the nth power. And then the 5, you can bring it downstairs because it's up top. You just bring it down. So it'd be infinite sum, n equals 0 to infinity. And so you would get negative 1 to the n, x to the n, 5 to the n, n factorial. And that would be the final answer. So just bringing the 5 down. bringing the 5 down. Do you all remember these from Calc 2 a little bit, maybe? Do you remember these? Yeah. Do you remember these from Calc 2? Yes. Did you like these? A little bit? No? Yeah. Yeah. Good stuff. When did you take Calc 2? Recently? A while ago?
About 2 years ago.
2 years. Wow. Wow. Hardcore. It's a long time. When did you take Calc 2?
Last semester, I think.
Oh, really? Okay. It's pretty recent. Do you remember this, kind of?
Yeah, very vaguely.
Vaguely, yeah. I know. Any questions on this one? Any questions? Yeah.
Minus 1n times x to the n, you split negative.
Like this.
X.
Yeah, I split the negative x.
Okay.
And the 5 came downstairs. Yeah, I split the negative x. Yeah, I wrote that as negative 1 times x, so it's negative 1 to the n times x to the times x to the n times x to the n. We should do a shifting problem because we have 15 minutes. Let's do a shift. Oh, so the other ones in the homework, they're a little bit different. Like they're all like this. Like they give you like this one's in the homework, and then there's like ln of something else. They give you the formulas in the homework, so you just replace the numbers. So I'll leave those to you. This is not going to be on your test, right? Because I just assigned them because there was nothing else to assign. So.
How's that the final answer when before we wrote it out?
Oh, we just leave it like this. Yeah, the homework wants it like this. It's a good question. The homework wants it like that. Yep. Let's do a shifting problem. And let's make it count because we probably only have time for one. So let's do like a hard one. I think that might be, yeah, okay. All right, it's on. Number 12. Let me see if I have it here in my notes. Just make sure it's hard enough. I don't, but I will just go with it. So infinite sum. I'll do it over here. So this is going to be part of the DEs, right? So this is going to be part of the DEs. So number 12. So we have infinite sum. Okay, infinite sum. N equals 1 to infinity. There's some other stuff too.
Can I read it to you?
Yeah, can you? Yeah. What
5n c sub n.
was the 5 outside?
No, it's inside.
So 5n.
C sub n. X to the n minus 1.
Oh wow. Okay.
And then it's plus
Plus.
infinite sum
Whoa.
n equals 0.
Perfect.
9 c sub n. X to the n plus 1.
Beautiful. Beautiful. This is really tough. So the question is to write it as a single sum, whose power involves with x to the k. So basically write with x to the k. Okay. Right with x to the k. This is going to come up in all of the series. Every single series we do, we'll have to do this. So it's kind of like a warm-up problem. After we do this, we can do a DE, right, which we'll do next time. So after this is a warm-up problem. Yeah, this is like the middle part of the DEs. This is a harder one though. Okay, so I picked a hard one to make it count. Okay, so solution. So there's a couple ways to do this. I'm just going to show you the way I do it. You can do it in your head if you want. I'm not going to do that. But I know there's people, I've had students who do it in their head. It's really hardcore, and sometimes they mess up. So the way I do it is I always focus on the k first. So step one is you call this k. So you let k equal n minus 1. Always. Right, always, every single time. So call that k. Call it k. Yep.
Why not k equals n plus 1?
Oh, because we want that to be k. We want it to be x to the k.
But there's this.
Oh, we're going to do that one over here. We'll do it in a minute. Yeah, we're going to do both. Oh, we're going to do both. Right. Then we have to solve this for n. So n, I thought you had like some other way of doing it. I was like, oh no. So when you solve it for n, you add 1 to both sides. You get k plus 1. This is really important. This is called shifting the index. You do this in a lot of like computer science classes. It's really, really useful math. And a lot of times people skip the steps, so it's worth seeing it. So you call it k, then you solve for n. Okay, now we're going to do it again over here like Rachel said. So now we're going to call this k. And you're wondering, well, why can they both be k? It's a dummy variable, right? It exists only inside this sum, right? If you multiply this out, there is no k, right? So then n would be k minus 1. K minus 1. So step 1, always just call that piece k, right? Every single time. Just call it k, solve for n. Call it k, solve for n. Always, every single time. Okay, that's the first step. So call it k, solve for n, call it k, solve for. This is tricky. This is really tricky.
You call it a dummy variable because it doesn't actually exist in the problem. Therefore,
Right.
it cancels out whenever you multiply it.
Right, like, right, exactly. The people call them.
It's just holding a spot, right?
It's holding a spot. Yeah. Yes, it's dumb. No, it's not dumb. But like, so like, right. So like, if you do something like this, you know, x to the n, n is called the index, right? But it is a dummy variable. Like, if you multiply it all out, there is no n, right? I could have put anything here. Could have put j here. Could have put I here. So people call that a dummy variable in mathematics. It's kind of like negative. Oh, it's a dummy variable.
So you create a variable to rename and, I guess,
And condense things.
categorize.
Yeah, to condense it in summation notation. So now we're going to rewrite it very carefully. So we have infinite sum. Write a little bit smaller. So now we got to think already from the beginning. So instead of n here, we need to have k, right? We have to have a k here. So this will be k. So let's see. When n is 1, what is the value of k? 0. Everyone see that? Because it's 1 minus 1. It's really delicate, right? So you take this and plug it in here. So you get k equals 0. Very, very delicate, right? So when n is 1, you get 1 minus 1, so k is equal to 0. Yep, very sneaky. And then infinity is just infinity. So, okay. So again, when n is 1, k is 1 minus 1, so it's 0. So now we're going to replace all of the n's with k plus 1s. So it'll be the 5 hangs out, so we have 5. And then n is k plus 1, so k plus 1. It's really easy to mess up in these. And then c sub k plus 1, so c sub k plus 1. And then we have x to the k, and that was the whole point.
I kind of see where this is going. We put k in both of them.
And then we can combine them.
We set k equal, and then you can actually move.
Right. Yeah, so right. The only way you can combine these is if they both have x to the k, and they both start at the same number. So you'll see that. So we first deal with the k, and then we look at the numbers and we do some more work. So step 1, doing it this way, is first focus on they both have to be k. All right, now let's go to this one. So let's see, we have plus, infinite sum. And I picked this one on purpose because it should be harder. So this is k equals, what do you think this one will start at? 1, right? Because when n is 0, k is 0 plus 1, so you get 1. So k is 1, right? K is 1. Everyone see that? So when n is 0, you get 0 plus 1, so you get 1. So 1 to infinity. Then we have 9, c sub, and then n is k minus 1. So this is k minus 1. And then we have x to the k, right? X to the k. So n is k minus 1, and then k is n plus 1. So we're here. So I purposely picked it so it's tough. So here's the bad part. This is 0, this is 1. That can't happen, right? Like if they were both zeros, we can just combine them and we're done, right? But we don't have so much time in class. So I figured let's make it hard. Actually, we do have time, right? Your test isn't until December 2nd in that regard, right? It's so far away, but that's good for you, right? We'll do a lot of DEs. It'll be good. We'll have like a couple days to do 6-2s. Blow out some crazy DEs. All right. So any questions up to here on this one, on any of the steps so far? So for
So now you're saying you have to make it start at the same place?
Yes.
You could have done that first?
Yes, I think it is. Yeah, it's harder for me. I mean, I usually don't. Yeah, there's people who do it that way. There was this guy, his name was Human. He would do it that way, and he would do it in his head. Yeah, he's really big too. Like he's huge. Human. Yeah, he's huge. He would carry around his English book. I'm taking English too. Like he was really smart at math, but like he was really bad at reading and stuff because he was from somewhere else. But anyways, yeah, Human. Crazy guy. Okay. So call it k, solve for n, and so we're here. So here's the trick. Make them both start at the biggest number. So this is 0 and this is 1, so we want them both to start at 1. Okay. So like if we had this, then our goal would be to make them all start at 2. Right? So if we had that, we start them all at 2, right? So make them start at the biggest number. Okay, so how do you do that? Well, what we do is we make them both start at 1. So this is starting at 0. So what we do is we plug in 0. We're going to write it over there. And we just start it at 1. So I'm going to start it at 1. You say, you can't do that. You'll see. We're going to start it at 1. So k equals 1. You get it? So we're going to plug in 0 and put the 0 over here. Yep. So we're going to start at 1. So let's do it.
It's a summation, so we're just adding that first 0.
Yes! It's a summation, so we're just going to plug in 0, but I'm going to add it at the end. I'm going to put it at the end. So we're going to start at 1 and put the 0 over there. So k plus 1, c sub k plus 1. I'll explain it again, no worries. It is really sneaky. Plus, just copy paste it, just start it at 1, then start it at 1. So this is a copy paste. K equals 1 to infinity, 9 c sub k minus 1, x to the k. All right, so this is wrong, right? Currently this is wrong, right? These aren't equal, right? This is not correct. So we plugged in 0 here, so let me pause and let you catch up. So it'll be plus. So we're plugging in 0 here, so it'll be 5 times 1, so just 5. Plugging in 0 here, we get c sub 1? C sub 1? Okay, this feels wrong. I haven't done this problem in a while. And then plugging in 0, we get x to the 0, which is 1. So we're plugging in 0 here, and that gives us 5c1 x to the 0. So you may say, what's going on? This is equal to this and this, right? So this sum starts at 0. So what did we do? We plugged in 1 and we got this. And then here's the rest of it, right? Because this is the sum from 0 to infinity. So if you plug in 0, you get this. Then if you plug in 1, 2, 3, 4, 5, 6, 7, the rest of the numbers, you get this. Does that make sense? Everyone get it? Mm-hmm. Any questions?
So you've just expanded the equation,
Mm-hmm.
right? And you've actually just done it once.
Right.
Put the answer there. So
Right.
You could do it multiple times.
Right, you could.
Go, where k is 0, and then whatever that equals, you put into the problem.
Yep. Mm-hmm. So this is equal to these.
You can get whatever k you want as
Mm-hmm.
long as you complete the problem for every single
Right.
iteration before.
Right. So let's talk about that because that's important. So let's say it was this, Matthew. Good question. Say it was this. This is going to come up. Say it was this. Then so if it was this, what do they all have to start at?
Well, if it starts at 0, that
No.
means
No. Because you have a 2, you want them all to start at what? 2. So that means here we have to plug in a 0 and a 1. And then here we have to plug in a 1. Again, if this is a 2 here, then they all have to start at 2. So here you have to plug in 0 and 1. And then here you plug in 1. Let's go nuts. What if there was a 4 here? This is like take-home test level. This gets insane.
Yeah.
Okay, make sure you work together on that.
All right, you need that at the 0, that at the 1, that at the 2, that at the 3.
Uh-huh.
They can call that 4 now. They need that at the 1, the 2, and the 3, and then call it 4.
That's it. You got it. That's it. Very good. So just to make the point, so if this was 3, you need 0, 1, 2, 1, 2.
But every iteration of k, you'd need the answer for every single.
Yeah, for every single one, you plug them in, and you have all these like extra annoying hanging out terms.
That's what those are.
Mm-hmm. That's what they are. This makes it harder. The more terms you have here, the harder the problems get. It gets really crazy. Okay, we're done, right? You just got to write the answer down now. So the final answer, now we can finally combine these, right? They both have x to the k. They both start at 1. So we have infinite sum, k equals 1 to infinity. We're just adding them up. Yeah, just rewriting it. So let's see, 5, I want to mess up today. 5k plus 1, c sub k plus 1, x to the k. Oh, no. I'm going to factor out the x to the k from both of these, see? So plus 9 c sub k minus 1, and then we have the x to the k like this. Right.
Where are your parentheses going on that?
Right here, the brackets. Right, so this one is this one, and this one is this one. Then what's missing at the very end? Plus 5c1. Yep. So next time, we still have a couple minutes, but next time, as soon as you come in, we're just going to do a DE. So now we're in the exact same spot as my night class, like same spot, like same place. Except it only took us 2 hours and 30 minutes. It took them 2 hours and 45. Oh, they get a 15-minute break. No wonder.
And they start so late. Probably all.
Yeah, I don't know. They're pretty wild. So it's a pretty wild class. So they're all like hyped up on Red Bull. Any?
Guys like that.
Yeah. Oh, yeah. Red Bull. Was it Grow Wings? Is that the?
Yeah, exactly. them before I went skydiving, just in case.
I can't drink energy drinks. I go crazy. I drink coffee. If I drink an energy drink, I'm like a maniac. I just, yeah. I used to drink energy drinks and teach before my night class. And then one day I thought I was going to have a heart attack, so I'm like, no more. So, any questions on this one? So that's the answer, right? That's the final answer. So during the weekend, try to finish 6-1. I will adjust the due date later today. I'll do it today because I'll definitely have to do it today. And I'll assign 6-2 later today. I'll just adjust the dates. So try to finish 6-1, right? So that's it. Yep. Turn this off. This thing was squeaking.
It was. It got a little better for the end, though.
Yeah, I know. I know. I want the old one back. You know, like they took a,
Somebody left you a note. Ding dong, bing bong.
Yeah. Huh, maybe it's not for me. Come on, move right.
Oh yeah, I guess it's an all-ear room.
So lame.
Maybe last class it was farther back this time.
It's a different robot.
It's a different robot. Yeah.
But it wouldn't have to spin as much if it was farther back this way.
No, I was there, but that's some physics stuff there, David. Oh, physics. Hey, what's up?